The next topic that we're going to cover is taking us towards applications of electrochemistry. So, we're going to talk about a basic electrochemical cell, which can also be called a galvanic or a voltaic cell, depending upon who you're talking to. And what they do is they convert chemical energy from spontaneous redox reactions into electrical energy. I don't know if you remember way back in lesson one, we talked about this whole chemical to electrical, and maybe you're starting to sort of see the light. Get it? Anyway, the key thing is that anytime you can get electrons to flow, electricity is produced. So a battery is a great example of an electrochemical cell. So really what we're going to be talking about here is how a battery works. Now, instead of me explaining it, I'm going to let another video explain it. Now, whether you like it or not, maybe I can repeat it afterwards, but I think they do a really good job. So there's a series of videos that were put out by the BC Learning Network, and they're great. I'd say the only downside of them is that they talk so slow, I get really annoyed. So I've already set my playback speed to 1.5. I have in the past watched these at 1.75 or 2, just saying. But I'm going to let this talk, and hopefully they'll do a really great job of slowly explaining electrochemical cells because I can sometimes talk really fast. Okay, here we go.
In this series of 2 videos introducing electrochemical cells, we'll show you how these are constructed, what the parts are called, and how they work. In part 1, we'll show you how an electrochemical cell is constructed, name its parts, and explain what happens at the 2 electrodes during its operation. We'll start with 2 empty beakers. In one beaker, we place a strip of copper metal. Some of the copper atoms on the surface of this strip are shown. In the second beaker, we place a strip of zinc metal. These metal strips are called electrodes. We attach wires to these electrodes and a light bulb between the wires. A light bulb allows current to flow through it. When there is sufficient current flowing through it, the bulb will light up. In the beaker with the copper electrode, we add 1 molar copper 2 nitrate solution. We'll show some of the copper 2 plus and nitrate ions present in this solution. Here we have represented 2 nitrate ions for each copper 2 plus ion. The ratio of these ions in the formula CuNO32. In the beaker with the zinc electrode, we add 1 molar zinc nitrate solution. We'll show some of the zinc and nitrate ions in this solution. Because of the 2-to-1 ratio of nitrate to zinc in the formula, we've shown 2 nitrate ions for every zinc ion. We add an inverted U-tube full of aqueous potassium nitrate with cotton plugs on the ends to keep the solution in. Notice as soon as we put this in, the light bulb lit up. At this point, we have included all that is needed to make this cell operate and produce a current. This tube with the KNO3 solution is called a salt bridge. We used KNO3 here, but any conducting solution will work, although we usually try to avoid ions which form precipitates with other ions. A conducting solution is called an electrolyte. We show a few of the potassium and nitrate ions inside this salt bridge. All electrolytes contain mobile ions. We have now constructed an electrochemical cell. Often a voltmeter is shown here rather than a bulb. A voltmeter measures the potential for current to flow in the cell, but the cell does not actually operate with a voltmeter here. When a bulb is present, current can flow through it, so in our discussion of how this device operates, we'll include a light bulb rather than a voltmeter. In discussing how the cell operates, we'll start by focusing on the zinc electrode. Let's look at one of the zinc atoms. It forms a zinc ion by losing 2 electrons which go into the wire, while the ion leaves the electrode. The process that took place can be summarized up here in a half reaction. We have zinc gives zinc 2 plus 2 electrons. Because electrons are lost, this is called oxidation. The electrode where oxidation takes place is called the anode, so in this cell, the zinc electrode is the anode. The process continues as more zinc atoms oxidize to ions and leave the electrode. Because zinc atoms are being oxidized, we can see that the anode is losing mass as the cell operates. Now we'll have a look at the copper electrode. As electrons enter the copper electrode from the anode, a copper 2 plus ion moves on to the copper electrode. This copper ion gains 2 electrons to become a neutral copper atom. This process going on can be summarized by the half reaction. Copper 2 plus gains 2 electrons to become a neutral copper atom. Because electrons are being gained, this process is called reduction. The electrode at which reduction occurs is called the cathode, so the cathode in the cell is the copper electrode. As more electrons come in from the anode, more copper ions move to the cathode, where they are reduced to copper metal. This process continues to occur, forming more copper metal atoms. Because more copper metal atoms are being formed, the mass of the copper cathode increases. Looking at the cell as a whole, because electrons are lost at the anode and gained at the cathode, as the cell operates, electrons move away from the anode toward the cathode in the wire. As they pass through the bulb, the electrons transfer electrical energy to light and heat energy. This is the end of part 1. In the next video, part 2, we'll examine the salt bridge, see how it works, and explain. This is part 2 of a 2-part introduction to electrochemical cells. Make sure you have seen part 1 to view this video. In part 2, we'll explain what happens in the salt bridge and why it is necessary for the cell to function. We will also review what we've learned in parts 1 and 2. In order to understand what the function of the salt bridge is, we'll see what would happen if we didn't have the salt bridge. As positive ions or cations are formed at the anode and enter the solution, an excess of positive charge would build up in the zinc nitrate solution. Notice we have a total of 4 positive charges and 2 negative charges on the ions depicted in this solution. And looking at the cathode on the left, as copper cations leave the solution and attach to the metal, forming copper atoms, a deficiency of positive charge would develop in the copper-2 nitrate solution. Notice we have a total of 4 positive charges and 6 negative charges on the ions depicted in this solution. Alternately, we could also take the viewpoint of negative charge. We could say that the solution around the zinc anode now has a deficiency of negative charge, and the solution around the copper cathode now has an excess of negative charge. The fact is that unbalanced charges cannot really exist in solutions. In every solution, the total positive charge of the cations must equal the total negative charge of the anions. So the process we described here could not really work with the cell right now. We'll drop a salt bridge into this cell between the 2 beakers. Some of the excess positive charge in the solution around the anode would be relieved by a gradual migration of cations away from the anode toward the cathode through the salt bridge. Similarly, some of the excess negative charge in the solution around the cathode would be relieved by a gradual migration of anions away from the cathode toward the anode through the salt bridge. So if we consider just the ions in the salt bridge, we can picture cations moving toward the cathode and anions moving toward the anode. And if we also consider the wires, we can picture electrons moving from the anode toward the cathode through the wires and the light bulb. So cations and electrons move toward the cathode, and anions move toward the anode. If we consider just zinc cations that came from the zinc electrode, they move into the salt bridge as they migrate toward the cathode, just like other cations. Now the copper cations that were already in the copper-2 nitrate solution around the cathode are cations too. So they will not enter the salt bridge, but will also move toward the cathode, where they will be reduced to neutral copper atoms. So we can summarize by saying that all cations move toward the cathode, and all anions move toward the anode, and electrons move from the anode toward the cathode through the wires. Here we'll summarize the main things you need to remember about electrochemical cells containing 2 metals and solutions containing their cations. Electrochemical cells are also known as voltaic cells. You may see this term in some textbooks. Oxidation always occurs at the anode. One way to remember this is oxidation and anode both start with vowels. For example, in the cell we've shown here, zinc metal atoms are oxidized to zinc ions. Reduction occurs at the cathode. Both reduction and cathode start with consonants. For example, in the cell we've shown here, copper-2+ cations are reduced to copper metal atoms at the cathode. If the anode is not made of an inert metal, it will lose mass as its atoms oxidize into ions. For example, this half reaction tells us that zinc metal oxidizes to zinc ions, thus dissolving into the solution. The cathode gains mass as cations are reduced to become metal atoms, which adhere to its surface. For example, in this cell, copper-2+ ions in solution are reduced to copper metal atoms, which stick to the surface of the copper electrode, thus increasing its mass. Electrons move from the anode to the cathode in the wires, from A to C. This makes sense because electrons are lost by the anode and gained by cations at the cathode. Cations move toward the cathode in the salt bridge. Both words start with cations and cathode. This makes sense because cations are produced at the anode and used up at the cathode. Anions move toward the anode in the salt bridge. Both anions and anode start with an. It is important to remember that reactions in an electrochemical cell are always spontaneous. In another type of cell we'll look at later, an electrolytic cell, the reactions are non-spontaneous. In all electrochemical cells, chemical energy is transformed into electrical energy. It is good to study and be familiar with all these facts about electrochemical or voltaic cells.
Awesome. So I really like that. It does stuff that I can't do, which is sort of animate what's happening. But again, just like they did, we're just going to summarize what's going on. So for your electrodes are your conductors, usually a metal, where the half reaction occurs. So the anode is the oxidation half reaction. It's the metal that loses electrons to form positive ions, and it loses mass as it dissolves. In this example here, which one was the anode? Okay, it was the zinc forming the zinc 2 plus and 2 electrons. The anode itself would be the zinc. I think it's labeled. I just can't see. Oh, no, it's not. Okay. I tried to take a screenshot at a point where it was showing most of the things. So for this example, the right-hand side is your anode. The cathode is your site of reduction. So this copper electrode is your cathode. So the electrode itself is the metal that is placed in the water, or in the solution, sorry, and then the reaction that occurs there is either the oxidation or the reduction. So the cathode is your reduction half reaction. It's where positive ions gain electrons to form solid metal, and that electrode gains mass as metal is deposited. So for us, that's going to be the copper 2 plus the 2 electrons forming that copper solid. So this one was the zinc solid forming zinc ions, which is why this guy loses mass. And this was the copper 2 plus gaining 2 electrons to form copper solid, which is why the cathode gains mass. And then the last thing to summarize is that flow of charge and the flow of ions. So the flow of charge is the electron flow. The electrons always flow from the anode to the cathode because the anode is where the electrons are lost, and they are gained by the cathode. So they go from the anode to the cathode. So this is the flow of electrons through the wire. If I wanted to figure out what a voltmeter would read, I could look for the voltage of these two different half reactions. So I have chosen zinc metal and copper metal, which are down here. And when I chose these two reactions, so where is my copper? Actually, copper's higher up, isn't it? There's my copper. So this is my copper 2 plus reaction. And then I've got my zinc 2 plus, which is down here. And to make this a spontaneous reaction, my reaction that's higher on the table is my reduction. So that copper 2 plus to copper solid has an E value of 0.34. Just put it here, 0.34. And then sorry, I hate it when my 4s look like 9s. My potential of my anode is my zinc running as an oxidation reaction. So it's going to be positive 0.76. So this is going to be plus 0.76, which is going to give me an overall potential of 0.34 plus 0.76 equals 1.10. Remember, I'm adding, so I'm going to maintain precision. So electrochemical cells only work if it's a spontaneous reaction. So you always have to make sure that your reduction is higher on the table than your oxidation. And it'll come out with a positive potential. And then the flow of ions happen in the salt bridge. They happen to balance out the charge in your two cells that are separated, and it always goes from the cations flow to the cathode and the anions to the anode, which is awesome. So my electrolyte for this solution is my potassium nitrate. So the cations that are going to, I can't say that without emphasizing cat. The cations that flow to the cathode are anything positive. So from the salt bridge, it's the potassium ions, but it's also the copper 2 plus ions, which get reduced at the cathode, and it's also the zinc 2 plus ions that are produced at the anode. And then the anions that are flowing to the anode, this solution only contains one specific anion, which is that nitrate. And again, we just always choose something that's not going to form or precipitate, so nitrate is often used. Okay. So now what we're going to do is we're going to construct some electrochemical cells. We will draw some, but oftentimes you don't need the drawing and you can just answer the questions with the knowledge you have of an electrochemical cell. So this first one is a cell is made up as follows. A piece of lead metal is immersed in a beaker containing lead nitrate, and a strip of aluminum metal is in a beaker containing aluminum nitrate. The metal electrodes are connected by a wire, and the beaker is connected by a salt bridge. We want to do the following. We want to write the balanced equation for the overall reaction, including the initial cell voltage. We want to talk about to which electrode the nitrate ions migrate, to which way the electrons flow, and toward which electrode do the aluminum ions migrate after being formed. But to do that, we have to figure out who's the anode and who's the cathode. And the only way to do that is the SRP. So if we go in here, and I really just need to clean this up. There we go. We are looking for aluminum and lead. We're often talking about metals in this part, so we're often looking at the bottom part of the table. And we just have to find where aluminum is and where lead is. So here's aluminum, and then lead is there. And then it's our job to make this a spontaneous reaction. So we are always going to make our higher reaction our reduction and our lower reaction our oxidation, so that it is a spontaneous reaction. In other words, the lead is going to be reduced and the aluminum is going to be oxidized. Reduction happens at the site of the cathode. So this cathode is going to be a lead cathode. And the reaction that's going to happen here is my Pb2 plus 2 electrons is going to form lead solid. And this is going to have a potential of negative 0.13. I'm just going to write it all down so we can close this table. And then my anode is going to be my site of oxidation, which is going to be my aluminum metal. So this cathode is, or this anode is going to be aluminum. And it is going to be oxidized to form aluminum 3 plus and 3 electrons. And the E is what's going to make it all worth it, because it's going to be positive 1.66 volts. Okay, so let's just finish off our diagram of this electrochemical cell. So we know that this is going to be our aluminum. Aluminum is going to be my anode, and lead is going to be my cathode. And so my solutions are going to contain, this is going to be my aluminum ions and my nitrate ions. Now, if we're going to be as good as that video is, we're going to put them in the right ratio, right? So it's AlNO3 NO3 3, right? So it's 1 Al3 plus and 3 nitrates. And on the right, it's going to be a solution of lead nitrate. So I'm going to have my Pb, again, 3 plus. Oh, dang it. This was Pb3 plus. Sorry about that. That's always a good thing to spot. Where was Pb3 plus? Pb3 plus. Or maybe this was a typo again. Let me just see. Is there a Pb3 plus? Because it could have been a typo, and then we could just change it. I don't think I caught that when I made my key. I don't think Pb3 plus is on this table. Yeah, that's definitely a typo. So let's just fix that. So this is going to be PbNO3 2, right? Okay, so then we're Pb2 plus 2 electrons. Ooh, good thing I didn't print the notes yet. Okay, so this is going to be Pb2 plus, like I thought, and then it's going to have 2 nitrates. Then you're going to have this salt bridge, which is going to contain some sort of soluble substance. So they often use sodium nitrate or potassium nitrate. This one didn't tell me. So I'm going to write my potassium over here and my nitrate over here, and you'll see why in a second. So now let's talk about the flow. The electrons are going to flow from the anode to the cathode. So the anode is actually going to end up with a positive charge, and the cathode is going to have a negative charge, which is what attracts those positive cations, right? And then the voltmeter, if you could attach one, would have an overall cell potential of 1.66 minus 0.13, which is 1.53. That is what that would read. And then let's talk about where everything else flows. So my electrons are flowing from my anode to my cathode, where the reduction of lead is going to happen. And then the flow of anions. All of your positive cations are going to flow to your cathode. So potassium's going to go this way and your lead's going to go this way. That's how the lead gets attracted to the negative lead electrode and then gets those electrons and is reduced. Now the aluminum is also coming up and around, right? So it's leaving the anode and going towards the cathode if it could enter the salt bridge. And then all of my anions, which is all my nitrates, are going to enter the anode and go from the cathode to the anode, right? Or the anions go towards the anode. Now, is that enough for my diagram? Heck yes. And you don't have to put too much in here, and you don't even need the diagram all the time. So unless they ask you to draw a diagram, this is all that you need to put in there. Okay. And if you wanted to, you could label this salt bridge or something, just so you remember what it is. Oop, if I could spell the word bridge. Bridge. So if I wanted to write the overall reaction, I have aluminum solid going to aluminum ions with 3 electrons, and then my lead is gaining 2 electrons and forming lead solid. So to write my overall reaction, you would need to balance the charge. Now, they don't make these so hard that you have to balance oxygens and everything. We just keep them really basic reactions, although you do have to know how to do all the other ones. But what I would do is take this reaction and multiply it by 3, and I'm going to take this reaction and I'm going to multiply it by 2. Now, because this is my simple reaction, I'm not going to put an intermediary step. I'm just going to put that my electrons are going to cancel out, and I'm going to have 2 aluminum solids and 3 lead ions forming 2 aluminum ions and 3 lead solids. And that's going to be my overall reaction. And then it wanted the initial cell voltage, which of course would be that 1.53 volts, which I found because aluminum was negative 0.13. And that doesn't change when we add coefficients. So even though here it's only 1 to 1 and here it's 2 to 2, that E value never changes. Charge changes, but E's never change. And then for my lead, it is that, whoops, I just reversed them, sorry. My aluminum was the 1.66 and my lead was the negative 0.13. Awesome. So then you can answer these questions. So like I said, if I hadn't drawn the picture, I could still answer these questions. The nitrate ions always migrate. They are anions, so they always migrate to the anode, which in this case is my aluminum anode. So we could add that in if we want, but it is just the anode, or more specifically, the aluminum anode. Which way do the electrons flow in the wire? Always from the anode to the cathode. So in this example, it would be from the aluminum to the lead electrode. And then to which electrode do the aluminum 3+ ions migrate after being formed? Cations always migrate to the cathode. So we'll say to the lead cathode. Awesome. Okay, let's do one more question. I recognize this is a very long video, but that's okay. Yeah, last video. So in here, we have a cell constructed using copper metal and copper sulfate and silver metal with silver nitrate. We are going to write the equation for the cathode half reaction, anode half reaction, overall reaction, and then answer a couple follow-up questions. To do this, you need your standard reduction potential table. And we are going to look up my new metals. So for this example, we are talking about copper, and this is copper 2+, and then silver, which is a 1+. So we just have to find them on the table. My silver is up here, and my copper 2+, we always go copper 2+ to copper metal, especially for electrochemical cells. And so my silver is going to be my site of reduction. So my half reaction at the cathode is going to be silver being reduced to silver solid. And then my anode half reaction is going to be my copper solid oxidizing to form copper 2 plus and 2 electrons. Let's include the E values as well. So my silver reduction is 0.80 volts, and my cell potential for my anode half reaction is negative 0.34 volts. So if I was going to write my overall half reaction or my overall reaction, I'm going to give and take 2 electrons to balance those out. So my overall reaction is going to be 2 silver ions and 1 copper solid is forming 2 silver solid and 1 copper ion. And the overall E value is going to be that 0.8 plus that negative 0.34, which is going to be 0.8 minus 0.34 is a E value of 0.46 volts. And again, that is a spontaneous reaction because the E value is positive. Awesome. Last 2 questions just as follow-ups. To which electrode do the sulfate ions migrate? They are going to, of course, migrate the anions to the anode. And in this case, my anode was going to be my solid copper. So it's going to be my copper anode. And then which metal is going to lose mass? It's whichever one is being oxidized. So that's going to be my copper as well. So the copper metal is going to be losing mass. Awesome. Go and practice a bunch of those.